So thanks for having me here today to talk about nitrate transformation in the Vedos. First, we talk about nitrate, which is quite a bit of talk issue in the state of Nebraska. A little bit about myself. Yes. So I started as a water research scientist back in the summer of 2021. I can still say that I'm fairly new, and I'm associated with Nebraska Water Center, Doherty Water Food Global Institute, with an academic home at School of Natural Resources. And my research is primarily focused on the critical zone, where we look into carbon nitrogen dynamics in the subsurface. But my association with water has been long enough. Since my teenage, I grew up in India, in a small town right here in the border of two states. And my primary work was to fetch water every afternoon for drinking and cooking purposes. And so was the job for me and my brother for quite a few years, actually. And that actually led to my education too. Water science is fairly new in India. So I was primarily doing chemistry, which was close to water. So I got my bachelor's in chemistry with an honors, then went ahead to get a master's in chemistry. And then finally, I had a chance to work on water during my PhD, where I worked as a material scientist, developing novel tools to treat water. Not only that, I had a chance to work actually in three different continents, Asia, Europe, and North America, across four different universities. And in my PhD, my primary work was to understand the primary source of contamination. Arsenic was a focus, and develop new technologies to treat it. This got both regional and national media attention, and also got me the opportunity to be a part of a research group in University of Cagliari in Italy for 2 years, where we developed a pilot plan for a community of 600 people. So over the years, I have been fortunate to work across the globe. And what I understood was that water quality issue is global. So be it a developing country like India or a developed nation like Italy or US, we have water quality issues, but the solution has to be localized. With that, enough about myself. After my PhD, I moved to Nebraska. This is where my research direction also changed. So if you look at my PhD research, it was primarily like water was already contaminated, and I was trying to develop a technology to treat it. So it was always a reactive process. And treatment is always costlier than preventing it. In Nebraska, over the years, during a postdoc and right now as the research faculty position, what I understood is that instead of treating, can we prevent water sources not getting polluted at all? Or can we refrain the contaminant from reaching there? So instead of taking a reactive approach, more of a proactive approach. And that is what today's story is about, where we will try to elucidate nitrate transformation in the Vedos. So before we jump into nitrate transformation, I'd like to share what Vedos zone is. I'm pretty sure most of you already know about it, but it's better to be sure that all of us know about it. So let's think this is the land surface. And if I start digging, I'll reach somewhere as an impervious zone. And on the top land surface, we grow our crops, we build our buildings. In between, if there is a groundwater source, you will see an aquifer, which is a saturated system. Water is flowing through sand and gravel. And if I dug up a well, I should hit the water right there. Now, this zone from the land surface until I hit that water table is called the Vedos, or unsaturated zone. Unsaturated with respect to water. So it can hold more water than it can get saturated. In contrast, the aquifer, which is called the saturated zone. In between, you may have localized clay lenses, which may have localized aquifer, but which will be considered part of that bigger Vedos zone. Just above the aquifer, you have something called capillary fringe. So if you recall your high school experiments where you have thin glass layers and water would rise up, basically that's what exactly happens right there, and you have a negative pressure. So water from saturated zone tends to rise up through those tiny holes within the soil pores and creates this unique zone called capillary fringe. So right now, although this is 6 months old, if you go and just type in Vedos zone with quotations in Web of Science, you will get close to 11,000 publications. And you will see almost 50% of them is associated with water resources. What I mean to say is that if I'm studying Vedos zone, I'm most likely studying it to understand water resources. However, most of the studies you will see is focused on right at the root zone. And there are two reasons for it. One is it's much easier to sample. You can just go out there and grab the sample. On top of that, most of the microbial activity tends to be in the top 50 centimeters. So that makes sense why you would want to go down deeper for the entire Vedos to not focus on nitrate only in the root zone at all. Now, where does nitrate fit in the Vedos, right? So when you talk about nitrate, the first thing that comes to mind is nitrogen. And when you talk about nitrogen, the first thing that comes is the air, where we have almost 70% nitrogen when it's breathing in and out every day. However, the dinitrogen that we see in air is not reactive. Until you see lightning, which can cause reactions, most of the time is not reactive. Here is the difference when you talk about nitrate. It's a reactive nitrogen, or in short, we call it NR, which can be reactive both biologically or chemically. So microbes can feed on them, or there might be some redox chemistry happening, which can also initiate reactivity. So if you look deep into all these reactive nitrogen sources, you will be seeing that there's inorganic oxidized forms, which is primarily nitrate and nitrite. This is what we're going to talk about today. Then you have inorganic reduced forms, which is ammonia, ammonium, and there is another set which is organic compounds, which generally we don't care about most of the time, which has urea, amines, proteins, nucleic acids of nitrogen in there. So how does nitrate get in here, right? So fertilizer is the primary source where we input nitrate into our soil. So if you think of how nitrate is getting lost, or nitrogen is getting lost from the fertilizer production until we apply in the crop, you'll see that if we produce 100%, almost 6% is lost right around the application parts. It might be just ammonium volatilization or some other gas formation which can go out. But we are primarily interested in this 47%, which is lost. Because primarily crops take up anywhere between 42 to 48%, and most of it is lost. Be it just for crop production or even for carnivorous diet where animal feed is being produced. That number is more or less fixed. And recent research has shown, along with our own research, that almost 18 to 30% of this nitrogen is lost in the vadose subsurface. And then it finally reaches the groundwater. And this is the USGS map, where you will see that nitrogen input, we have high nitrogen input and high aquifer vulnerability. And you can see right here, the state of Nebraska sits in that red hot zone where we have high nitrogen input and also high aquifer vulnerability. But then can we think of just, okay, fine, let's stop using nitrate and we are done with it, right? No, that's not so easy, because nitrogen is the key that unlocks the global food system. And I always prefer using the CEN editorial that came back in August of 2023. Nitrogen fertilizer pollutes drinking water and feeds nearly half the planet. So unless we have a source where we can match the crop production that we are getting right now or surpass it without using nitrogen, we have to continue using it to make sure that food security is still maintained. But luckily in Nebraska, as we have been focusing on nitrate consumption for quite a long time, we have a huge data set. And this study back in 2019 by Junta et al. Also did show that not only we have huge data set, but the data set can be divided based on the type of irrigation that we're using. So generally the gravity side, irrespective of east or west, showed much higher nitrate in our groundwater resources compared to center pivot, which is not surprising because gravity uses way more water compared to center pivot. And it looks like in the east part, there was a rise across a few decades. And you can see this purple color, which is pretty high in nitrate and along the Platte River and northeast Nebraska. So you will see that quite a few articles about nitrate in groundwater are already available, be it in Nebraska or Oglala Aquifer or North America. However, before the nitrate reaches the groundwater, it has to pass through this vadose zone, which we just described, from the land surface until hit the groundwater table. And how important is that? So this was a paper that came in 2017 in Nature Communication by Scott et al., which kind of maps the amount of nitrogen stored in the vadose zone. And it does from 1925, so just around the advent of Haber-Bosch process, I think back in 1913, 1914 when that started. And then it goes to 1950, 1975, 2000. So you'll see the countries which started adopting this easily available inorganic fertilizer started to show higher amount of nitrogen in their vadose zone. Specifically, Europe started right around Germany, so you can start seeing that. Then America adopted, we can start to see it here. And it is increasing. India, China, they adopted around 1960s, 1970s. You start to see how things have started storing nitrogen, nitrate in the vadose zone. This is like a ticking time bomb, in the words of Scott et al., until it reaches the groundwater. And it's pretty obvious that countries which adopted inorganic fertilizer before started seeing more and more nitrogen in their vadose zone as the time progressed. And all of this addition, people are already talking about that, has this high amount of addition of artificially produced nitrogen has changed the nitrogen cycle. So this is a nice article in Science by Galloway et al., where they talk about how fertilizer is moving across different places around the globe and how much amount is getting moved, which is getting applied, which was not supposed to be part of the Earth nitrogen cycle, right? Because this was externally produced and then being applied, and how it is getting used by the grains also as it is transformed. And if you do the maths with these numbers, you will see that almost 21% of nitrogen is being applied through our Haber process, which is needed again to secure food security. So all of this definitely has an impact on the nitrogen cycle that we think of, or that we know of, that we have studied. However, most of the study on nitrogen cycle is again focused on the root zone, where we have very nice understanding. We have multiple missing nitrogen pieces as we go down in the deep reduced zone. So looking at this cycle right here, DON is dissolved organic nitrogen, NORG is organic nitrogen, so all of the reactive nitrogen component. And this talks about different processes that can be associated with it. And the rate is in microgram N per gram per day. So you can see that we have a very good understanding is what exactly is happening in the root zone, though we have some questions. But for the Vedos zone, we have just one thing, leaching, some accumulation, a big question mark there. So we really do not know what is happening. And most of the time when you talk about that Vedos zone, right after that nitrate has lost the root zone, we think it as a roadway for the nitrate to pass through until it reaches the groundwater table. Even most of the studies have been focused on tracking the time it will need for nitrate to pass through this thick Vedos zone layer until it reaches the groundwater table below. But this notion changed from a recent study which we conducted in Hastings, Nebraska, not far away from Lincoln. What we did, along with working with Hastings utilities, we identified 32 Vedos zone coring locations. And to our advantage, all these 32 cores were in different locations. We had pivot irrigated locations, we had gravity irrigated locations, and we had some dry land along with some samples right at the city park area, as you can see here, Matt collecting samples. What we did is that as soon as we got the data, we started looking into irrigation pattern, especially focusing on the Gunta et al. Research. And we found that yes, gravity invariably has higher amount of nitrate expected. Water is needed to move nitrate, more water, almost 65 to 70% more water. So you're going to put more nitrate in the Vedos zone. Pretty easy there. Things become complicated because in this project, we started looking at ammonium N also, another reactive form of nitrogen, which was the reduced form. Surprisingly, the low irrigation system, which is the center pivot, was having way less nitrate, but was having quite a high amount of ammonium in there in the sediments of the Vedos zone. So collectively, this is around 800 data points of the soil samples. Gravity surprisingly was having less. But if I add these two up, which is the inorganic nitrogen or reactive nitrogen of inorganic form, they are not significantly different. So something was happening, which you do not know. In the pivot, it might be transport, but then the argument can be that if it is transport, why it is not getting transported faster in gravity where you are putting more water? In nitrate, we understand nitrate is negatively charged, your soil is negatively charged. Think of a magnet with North Pole and North Pole. If you try to bring it together, it will be forced out. Exactly the same thing happens with nitrate. Your soil is, particles are negatively charged, you have a negatively charged nitrate. Nitrate is pushed out, and which we call anion exclusion, and it transports pretty quickly. Ammonium on the other side is positively charged. Think of North Pole and South Pole. It tries to stick with the soil and doesn't want to move through the soil profile so quickly. So this was surprising. That is it transport? Because ammonium is applied, or ammonia is applied as a fertilizer source. And it is more interesting to a chemist like me, because nitrate is the most oxidized form of nitrogen. You can see 3 oxygens sitting right there, whereas ammonium is the most reduced form of nitrogen. So you are at the 2 extremes, and you are seeing these 2 extremes in the Vedos zone sediments. However, this was just a mere observation, right? So we were not sure, is it just a correlation? And correlation may not be causation, and that is where that nitrate transformation piece comes into play. Now, why this is important? So why this is important if it is not a mere correlation, but you can change the form of nitrogen in the subsurface? Because we have to then rethink the approach that we have. We think nitrate is leaving the root zone, reaching the water table right away. We're not even focusing in that thick layer, which is doing something nitrate, right? Because if we understand that, then we can develop technologies where we can proactively develop ways to eliminate nitrate within the bed ocean, which is the groundwater table. And that is where we want to shed light and bring in the understanding to create these proactive technologies. Can we eliminate nitrate in the bed ocean before it reaches the groundwater? Can we use the reactivity of bed ocean to our advantage? But to answer this and to have all of this, we have to first prove, is it just a mere correlation or is it a causation effect? To do that, we went back, collected fresh set of cores very close to Hastings, but not exactly in Hastings, at York County, right here. And this producer within the upper blue NRD, and this producer provided us the historical data that he had along with the amount of fertilizer wasn't applied. It was a monoculture corn, so corn after corn every year. One key thing was that we had a weather station nearby this location. We collected 2 deep bed ozone cores around 70 feet, which we bought back in the lab. So as you can see, this comes in this kind of slits. This is a bit thicker. And then what we did, we recreated the bed ozone system. How did we do it? Taking this entire liner, we sliced out 5.3 centimeter of it and tried to pack it in this 150 centimeter column, taking 10 centimeter at the top. So kind of condensing the 70 feet of bed ozone to a manageable 5 feet sized column. Why do we want to do it? Because if we really want to study, we have to have controlled system. After packing this up, we made a groundwater table using the groundwater collected from the farmer's field, completely sealed it, made the groundwater constant, and put in this kind of thin probes which can collect soil pore water. These are called Dyson CSS, and this has been designed to collect pore water from undisturbed soil pores. And in this case, it was technically disturbed because we were slicing it off, but those 5.3 centimeters were intact. So those things were not disturbed per se. And this was a pivot irrigated field. So what we thought that, okay, fine, if it's pivot irrigated, we will continue pivot irrigation. Along with that, 3 of the columns, so we made 6 columns, 3 of the columns, we converted it to rain fed only. So we reduced the irrigation water completely. And that is where the NOAA weather station came in handy. So as soon as rain or snow was happening there, we were applying artificial rainwater that you can see in this blue lines for that 160 days. And we knew from the farmer when he's irrigating. So we used that irrigation based on inches he provided. We converted into ml and we applied that on 3 of the columns along with the rainwater. So all the 6 columns received rainwater, which was artificial. So we knew exactly what we were putting in. There was no nitrate in it. And then 3 of the columns also received additional irrigation water based on what the farmer was doing out in the field. As expected, we first looked into the nitrate concentration in the groundwater. It was not surprising that the irrigated one showed higher nitrate concentration for more number of days compared to the rain-fed system. Because irrigation is putting more water, so nitrate is going to be flushed out. Makes sense. Ammonium varied quite a bit. And this is the groundwater. So groundwater sample was collected using those thin rhizome probes that I mentioned. So it was matching with what we should have observed. Ammonium concentration varied. We did not know what was exactly happening with ammonium there, but we did see that it was not constant, or it was not like a particular irrigation system was driving it. But the primary question was, does nitrate transform? Right, so that was we wanted to prove. So this black line that you are seeing, so this is the column depth. If I convert it to the bed ozone depth, which was around 68 feet, this is the bed ozone depth. This black triangle that you are seeing was the pre-soil or the day 0 soil. So as soon as we got the soil, we collected subsample, we were packing it in the column, and we measured the amount of nitrate and ammonium doing a KCl extraction. So this black line that you are seeing with the triangle was the pre-soil or day 0 soil nitrate concentration. This one, the red one, is the rain-fed system, and the square is the irrigated system. So we definitely see there is a huge decrease in nitrate concentration. Remember, we did not apply any external nitrogen. The nitrate that you are seeing in the bed ozone was as collected from the field. The only thing that we did was we applied an organic solution to emulate or simulate as if corn is growing on top of it, and corn roots would release this organic carbon, which goes to the root zone because it needs to uptake nutrients. That was the only thing we did, and that did not have nitrate in it or ammonium in it. This black line in the other side, where again, this is the column depth, this is the concentration of ammonium, this is the day zero soil or the field soil ammonium concentration. Look at the rain fed, right at the top 5 feet of Beddoes zone compared to top 25 centimeter in the column. Significantly higher ammonium was observed, even higher than what nitrate was there, right? So something was happening to nitrate. Of course, it was not forming ammonium because ammonium concentration is way higher. Same thing was also observed in pivot, but much on the irrigated side, but lesser than what it was in the rain fed. So if less water is there, it is kind of driving a reaction which you do not know, making more reduced reactive nitrogen, which is ammonium. It may or may not come from nitrate. Even if it comes from nitrate, it will be just part of it because nitrate was just 8 microgram N per gram or 8 milligram N per kilogram or 8 ppm, whereas ammonium we are seeing almost 80 ppm. So it cannot be coming from nitrate alone. One more thing we observed in that small experiment was that we were measuring any fluctuation in oxygen saturation right at the groundwater Beddoes zone boundary. Actually, the capillary fringe, which I explained earlier. So we had probes to measure if there's an oxygen saturation changes or not. What we observed was oxygen was almost zero, which is expected because there should not be any oxygen down there, right? However, as soon as there was a rain event at the surface, which this blue line is showing up here, and this is the amount of water applied, and this is where we had our irrigation started. We started to see there is a spike in there, but as soon as that intense irrigation started right here, we started to see within a week, there was a huge jump in oxygen saturation right at that groundwater Beddoes zone boundary. Something unique was happening right at the groundwater Beddoes zone boundary. But keep in mind, this is a simulated column, not a 670 feet Beddoes zone, just 5 feet. So this may or may not be observed in the real world. But then when I started talking about it with our peers, we started to learn that, yeah, this is the observation that happens even if the groundwater is not fluctuating, and they have been observing this in the northeastern part of our country for quite some time now. So in this small experiment, one thing that was certain that Beddoes zone is reactive. So thing we thought that nitrate, as soon as it leaves the root zone, it's going down there to the groundwater. We just have to calculate when it reaches there. That's not true. Something is happening. What is happening, we still do not know clearly. Low water input drives reactions, which is surprising because you need water to drive reaction. But in somehow, if you have less water, conditions are more conducive within the Beddoes zone to drive some of these reactions. And surface water application, be it precipitation, irrigation, or higher amount of irrigation, is linked to oxygen saturation fluctuations in the Beddoes zone or at the capillary fringe. But this experiment does not answer that key question that I asked initially, that okay, I am applying so much amount of fertilizer on the surface. How is it affecting the groundwater nitrogen cycle in the Beddoes zone? We have studies about the root zone. So to do that understanding of nitrate transformation due to that application of fertilizer, we had to take a different approach. Again, a controlled Beddoes zone experiment, but this time we did not use Beddoes zone codes from a cropland. We went to Homestead National Historic Park, where we identified that they do not have any agricultural footprint, at least for the last 50 years based on history they had. And it might be like forever too. We went there, we got permissions from Federal Park Agency, once approved, collected 6 Beddoes zone cores within a 1 square meter area so that there's less spatial variability, and again created columns. But as this Beddoes zone was just 10 feet thick, we had one advantage. We could compact it within the 5 feet column much easier than the previous one. So we took the same approach, but in here, instead of having the root zone thin slices, we kept the entire root zone, the top 2 feet intact. So whatever was coming, we exactly put it in the column. Rest of the 8 feet was compressed to make that, I think, 90 centimeter of the column length. And then we divided that into 2 irrigation practices. Furrow or gravity irrigated, which used significantly higher amount of water that was applied based on the USDA NAS database for Nebraska. And 3 were pivot irrigated. And all 6 of them, we applied 180 kilogram per hectare of N15 labeled nitrate. The reason we chose 180 kilogram N per hectare, that Hastings study that I showed, comparing pivot and gravity, over there also they used close to 180 to 190 kilogram N per hectare across both irrigation systems. And then to ensure that there is no root growth below there, we used a specialized kind of a system that does not allow root to go to the deeper bed ozone. So we can keep the root within the top 2 feet only. Finally, to ensure that it looks like a bed ozone, we wrapped it around with a cooling jacket, because generally if you go 2 feet below the surface, temperature does not change that much. It remains somewhere around 18 plus minus 1 or 2 degrees centigrade. So we wanted to make sure that that happens with our simulated bed ozone column 2. And this is what you can see, that we had this cooling jacket with a cooler, continuously water was cycling back and forth. And we did not use root exfoliate this time. We actually did grow corn on top of it. So as if a native parare is being converted to cropland. And this is the entire set, because we had other experiments going on there, and just seeing at the crops, you can see which was dry land, which was pivot. Because dry land was always short, but we are not going to talk about that other experiment. We just focus on that 6 columns with gravity and pivot. And we started to look at the groundwater again. Expectedly, furrow irrigation uses more water. Nitrate started to show up in the groundwater pretty early. Pivot did not show nitrate in the groundwater at all for all the entire sampling events that we did. So this experiment started, let's say, at day 0. We gave around 2 months for the column rain event to continue so that the column is well equilibrated. And then on day 60, we started collecting groundwater samples along with other locations also, but we'll not talk about other locations today. And what we started to see is that, as expected, furrow was showing higher nitrate. No. Ammonium, again, fluctuated quite a bit, as we observed in the previous study where there was no corn in there. But we also started looking at some transient species, hydroxylamine. If you do not know hydroxylamine, when ammonium is getting converted to nitrate, it passes through this transient nitrogen species called hydroxylamine. The formula is NH2OH. It is, you will generally not observe it because it's transient, but it gives you an idea to identify which pathway the nitrogen cycle is going. So if I see hydroxylamine, that means what? There is some ammonia which is getting converted to nitrate in the system. So we use that as our marker to see, do we observe hydroxylamine at all or not? We did not put ammonium as our fertilizer here. It was all nitrate. And I'll show you that the pre-soil contained almost no nitrate in these systems. We started seeing hydroxylamine in the groundwater. And we had to measure it very quickly. So as soon as you get it, within half an hour, we will have to measure hydroxylamine. Otherwise, it will just vanish. In the capillary fringe pore water also, we started seeing hydroxylamine. So this is the hydroxylamine concentration in the y-axis and the sampling day 60, 90, 120. And this is when we harvested our corn in those columns and took out all the columns. In the furrow irrigated, groundwater showed higher hydroxylamine, though not significant other than one sampling point. However, in the capillary fringe, pivot irrigated site had significantly higher hydroxylamine compared to furrow irrigated site. Why? We still do not know. So if you ask me, I'll say I do not know as of now. Interestingly, more clear picture was available when we started looking at the sediment profile. So this y-axis is the actual column length, and this one is the bed ozone depth. If I convert that column into an actual bed ozone depth in Homestead National Park, this is how it would look in the bed ozone depth wise. As I mentioned, we try to keep the top 2 feet intact. That's why you'll see that there's a division here, right, a break here, and then we compress this 8 feet within this region. This is again that triangle is our pre or day 0 soil, nitrate or ammonium. As you see, there is almost no nitrate in the bed ozone profile, which was not affected by any human activities. After one growing season, technically this is like one growing season, we see nitrate accumulation both in the pivot and gravity irrigated system at the top 2 feet. Of course, the topmost soil has highest, you have less, but nothing changes at the deeper profile, which is around 2 to 8 feet depth. Ammonium was there initially, as you can see. It also started accumulating, but it accumulated much deeper than nitrate. Again, no ammonium was applied on these columns. They only received nitrate as their fertilizer source. What exactly changed was organic nitrogen. Organic nitrogen was again much less, right, around 700 to 800 milligram N per kilogram. But within one growing season, irrespective of the irrigation system, we almost tripled in our organic nitrogen concentrations. So if I go back in the history, think of the day when you started putting crops in here, started irrigating here, this is how exactly our nitrogen cycle was changing. And of course, by now, when we have 120 years of continuous irrigation practices, it has changed quite a bit. We need to understand that also, which we are not going to talk about today, but we are trying to understand that too. If you look at the total nitrogen, which combines all form of nitrogen, you will see that almost 95% of the total nitrogen is actually organic nitrogen. 5%, even less than 5% in some locations, is nitrate or ammonium. Even after first growing cycle 2, almost 90% is organic N. A thin sliver is nitrate, which we are so worried about in our groundwater system. We did not stop here. So in this year, we not only measured nitrate ammonium, we started to measure all the nitrogen pools that we know of as of now. We also measured hydroxylamine. We did not see much of variability, but there was occurrence of hydroxylamine. What was interesting was carbon. If you look at the water extractable carbon, this is the most labile carbon which microbes really like to eat, like a candy. We had water extractable or DOC or dissolved organic carbon in the soil throughout the profile. Of course, it was much less as we went near the water table compared to the surface. This was not significantly different when we were irrigating with pivot. Gravity did increase quite a bit, but total carbon, there was a huge increase. This is not just the dissolved organic carbon, but the total amount of carbon. In the surface, I understand we have a lot of plant material that will contribute to the total carbon, along with the organic carbon. But even at this depth, which is around 4 to 5 feet in the actual vadose zone, we were seeing much higher amount of organic carbon. So when we study vadose zone, what we can think of is that vadose zone is not only can act as a time machine where you can predict when nitrate or other contaminants can reach your groundwater table, but if you closely look into it, it can also act as a time capsule. So what practices happened 50 years, 60 years, 70 years, 80 years, or a decade ago, you can have a marker down there, provided if you are looking into the right directions. So before this kind of work that we started doing, it was simply, okay, nitrate is living, reaching out there. But we clearly see that no, nitrate is not living there. Most likely nitrate is first getting converted to organic N. And that ammonium that we are seeing in our vadose zone crop course from the cropland is most likely coming from that organic N. So to sum up, again, this is an ongoing research, to sum up what our observations has been over the past 3 years, is that we can clearly say vadose zone is highly reactive. It is not a non-reactive locations within sandwich between the land surface and the saturated zone of the aquifer. To really understand the nitrate problem, we need proper nitrogen budgeting. So just measuring nitrate in vadose zone core is not going to tell us how quickly our groundwater is going to get contaminated, or neither going to give us an idea to develop proactive technologies where we can eliminate nitrate in the vadose zone before it reaches the groundwater table. It is very clear, organic N pool is the most significant pool of nitrogen, measuring almost from our data, we can clearly see it's almost 80 to 90% of the total N that we are seeing. And most likely the ammonia that you're observing in a repeated cropland, which has been irrigated, fertilizer has been applied for almost 30 to 40 years, even more, is most likely coming from that huge organic pool that has most likely come from other fertilizer and converted to ammonium slowly. And high residence time is most likely driving this reaction. So of course, there might be some other microbial entities too, which can convert nitrate to ammonia. As of now, we have not observed that, but that does not mean that may not happen. So to sum up again, vadose zone reactivity is true. Really understand the nitrate problem of groundwater, we need to understand all other nitrogen reactive species. With that, I'll stop here and thank everyone who helped do this research and is continuously doing the research, and especially the funding agencies who have supported all this research. And I'm ready to take questions. And again, I want to keep it more open because we have very limited research on vadose zone reactivity. So really good to hear from all of you. Thank you.
One quick question. So Hydroxylamine, more like hydroxylamine hydrochloride, is more specifically is a strong reducing agent. Do you think that hydroxylamine is like in the pores is present long enough to react with other components of the sediment like iron?
So I did not show it here. So Jeff, we did some geochemical equilibrium modeling to really see that if this is happening. And if you're very small, you can see that the hydroxylamine was actually less than 1% of the total nitrogen pool. So even though small amount of hydroxylamine can drive some of the reactions or not, we were seeing that once that reducing agent is getting oxidized, it is driving some reactions which is reducing some other components in there. So we started to see difference in arsenic concentrations along with some reduced iron and manganese. I did not show that, but we wanted to just focus on nitrogen today, but we were seeing reduced iron quite a bit, reduced manganese, Mn2+, along with some reduced arsenic in our pore water samples, which we measured, partly thanks to you.
Okay, thanks.
Did you do mass balance on nitrogen before and after on that last set of experiments? The nitrogen available in the prairie soil versus what it was after you applied nitrogen?
So if I understand correctly, Dan, you were asking that we applied that 180 kilogram N per hectare, and then it is 200 pounds per acre. Did we do a nitrogen balance with that?
Correct. Yeah.
We tried to do it. We were able to return back almost 85 to 90% of the nitrogen with everything that we measured. Unfortunately, we measured nitrous oxide emission as a snapshot. So if we include that, we are reaching 90%, but I'm assuming there might be some nitrogen gas that also is getting formed, which we did not measure at all. But yeah, we did not get like a 100% mass balance based on what we observed before plus after.
Okay.
But I know we did bromide tracing, so we're seeing bromide coming out in the groundwater.
Any thoughts on the physical composition of the vadose, the hydraulic properties, the porosity and grain size and so on as sort of reactive surfaces? Is there, how might that impact results and sort of transferability to other sites?
That's a wonderful question, actually. So that's always a challenge, the spatial variability that we see. And even if you look at these two experiments, the first experiment vadose zone depth was almost 70 feet, the next experiment was 10 feet. The second site, or Homestead National Park, the soil was quite different compared to the soil that we did see in the UNRD vadose zone course that we collected for the first experiment. One good thing is that if thermodynamics is valid, we should see those reactions, provided it matches the other conditions required for that reaction. However, we need to ensure that this is a true fact. So part of that project which USD and IFA is funding, we are collecting vadose zone cores across the state. I think we have completed close to 12 NRDs, 13 NRDs now, so we have 10 more NRDs to go, where we can compare, not only we're collecting under different irrigation practices, that is dry land, pivot and gravity, but we're also collecting across the state. We have a good weather variability from east to west and also good lithological changes. And we can see if we are observing that same thing, that pivot irrigation is reducing nitrate in the vadose zone, which is good, right? So if we reduce nitrate, if it's forming ammonia, ammonia is much slow moving contaminant. And it might be, by the time it reaches most of the groundwater, it might be completely used up by some other microbes to some other form. So if vadose zone centric technology or proactive technology doesn't have to be, you have to go to the vadose zone. You can do something on the surface, provided you can prove that this is going to happen in the vadose zone in a repeated way. To sum up, it will affect soil ecology, will have changes, because if you have like a clay layer, your nitrate will accumulate there. If you have a sandy layer, nitrate will move much faster. But if we are able to recreate that time boundary that we're talking about, the reactions, we should see those kind of reactions irrespective of the soil ecology.
Have you characterized the microbial composition or the change in community population between prairie vadose zone versus the developed profile?
So we started doing it, and I can tell you that as you go deeper, getting good quality DNA is pretty hard. So I'm working with one of my collaborators, Dr. Dan Miller, in USDARS. So we now think that we have established method, like the hydroxylamine measurement also, we do not have established method. So we work together to develop that method so we can measure it. So now we know that we have established method where we can measure microbial population or diversity along the soil profile. Now it has changed from when a native priority land is converted to a cropland.
So you did percent carbon and then total organic nitrogen. I wonder if most of that is protein.
It can be, yeah. It can be, but that protein still, as you can see, Dan, is that it is increasing significantly when you're converting an native priority to a cropland. So
Yeah.
that means the roots or the crop is bringing something which is not present in a native priority, which is primarily grassland where we collected the sample from. So something is different. Of course, corn is also type of grass, but something is different with corn roots that is most likely bringing in, or whatever fertilizer we added. So it might be multiple things that is doing. Yes.
Hi. So you had mentioned that a lot of research on the Vado zone was really focused on it as like a stepping stone between the topsoil and then getting down to the groundwater and kind of thinking about it in the transport of specifically nitrate. And so kind of if these transformations are happening, how does that fit into, like, if it's happening at a large enough scale where hypothetically some of these selections at the surface, so irrigation or management, are impacting how it's transformed in the Vado zone and then eventually transported, how does that fit in eventually maybe to how we understand the transport? Like, do you kind of see this being a really big lever on that, or not? I don't know,
That's
kind of some thoughts.
That's a great question, Rick. So I'll quote one of my friend. She said that people who do not believe their data is the person who is collecting it, and people who believe in the model is the person who is developing it. I'll leave it there, but though I work on both data and modeling. So you're right, the current models that we have about nitrogen transport primarily focus on that transit time. They do not look into different nitrogen pools that this nitrate can convert to once nitrogen has left the roots. So as pointed out, that they will look into the soil lithological system, how hydraulic conductivity is happening, how quickly the water may move or may not move. So it's always trying to relate water movement with the nitrate movement. And that is the way it is looking. So sometimes it is true, sometimes it may not be true where you are seeing this kind of transformation happening. Now, this is a very limited set of data across the vast Vado zone that we have. So we have to first confirm that is this happening everywhere or not. So if it is happening everywhere, then we have to start to think how can we start looking into the model source code and incorporate these new reactions that we are finding, which is not available right now, so that we can give our stakeholders much true number about when the nitrate will reach the groundwater. Or will it reach at all if I'm changing this to a different kind of practice? Like if you recall the very first presentation that we had in the Nebraska Water Center seminar series, in Lower Loop NRD or
Little Platte North.
Oh, yeah, so Daryl was here. Daryl talked about they are incentivizing pivot irrigation. So these are all the observations that we're seeing that, okay, if I'm going to pivot irrigation, I'm producing less nitrate in the Vado zone. So these are data-driven changes that we are slowly implementing, not only in the policy side, but also we have to start looking into those core models that we use and how can we incorporate this new finding that no, Vado zone is not non-reactive, it is reactive, and we have to start looking at different nitrogen pools that it can transform to, because then you get the true picture of when nitrate is actually reaching there. And that is, of course, a goal that we have in our mind as my own long-term research too, that how can we make the model as a 2.0 version or 3.0 version where we have this unique reactions that we did not think of previously included. And that is part of, again, being proactive, right? So if I know that, okay, fine, my water is going to get contaminated 10, 20 years, I might be more well prepared to manage it. Then it certainly starts showing up in my water resources. I know it was not a great answer to give you with this context, but yeah, we are not yet there where we have modeling capabilities to incorporate this kind of reactions.
Any other questions?
I got one more.
Yeah, go for it.
So you tried to take the vadosome and bring it into the laboratory. Now that you've made some very careful measurements, are there ways that we can do a better job of measuring what's happening in the real world with the vadosome?
That would be the best thing to do, right? Because you always back in the mind, you always have that question, right? So I compressed a 70 feet vadose zone to a 5 feet. That oxygen fluctuation that I'm observing, is it really true? And will it happen in the field or not? Because we're not measuring in the field. So luckily I had some colleagues who said that we're seeing it in the field also, but I have not seen in our aquifer system that is it happening or not. So that would be the way forward, is how can you start monitoring this lab-based simulations in actual vadose zone system. Like Hastings is a good place to be because we have historical data there where Paulding had 2011 data, then we had the data from what I shared right now. And if we do again new set of corings and install some of these probes where you can get the temporal differences in oxygen saturation, we can start to think how it is changing, and that can be a segue to really develop this novel vadose zone technology to eliminate nitrate right there within the vadose zone. Of course, keeping in mind that we're not creating other contaminants like uranium and arsenic while I'm trying to remediate nitrate, but it'll be good to have it, and that is in my wish list. But of course, doing this kind of field-based research, you need much more funding than what you'd be able to do with bringing the field to the lab. Yes, more research funding is required for this kind of research.
Well, thank you all for joining us today for our last seminar, and let's thank everyone again for this presentation.